In this lesson, we're going to talk about approximating the binomial with a normal distribution. In our previous lessons on binomial, we learned that the probabilities associated with our binomial experiments are readily obtainable from the formula. We had the formula of the binomial where we have x, and we knew n, and we knew p, our probability of success of the binomial distribution. And we also used the binomial tables, but what we saw was that was good when n was small, but as n got larger, it was difficult to obtain that because there wasn't always a table and sometimes the formula got cumbersome. However, today, with a lot of computer programs and statistical packages, it's very easy to get binomial at a large number. But for years and years, the binomial at large n was approximated with a normal distribution. And so it's important to learn the relationship between the binomial and the normal distribution. The binomial distribution is discrete, which, as we talked about the normal and we talked about continuous, we say you can't get a probability for an exact number because you have to take the area, and we need an interval that we take an area of. But the normal distribution is often a good approximation to a discrete distribution when that distribution takes on a bell curve, because we can create an interval. The binomial distribution is nicely approximated by the normal in practical problems when one works with a cumulative distribution function. We now state a theorem that allows us to use the areas under the normal curve to approximate the binomial properties when n is large. So again, this is when n. So if x is a binomial random variable, and we remember that the mean is equal to n times p, and the variance was equal to n times p times q. And remember, q is the probability of failure, which is 1 minus p. Then the limiting form, so our z transformation would be equal to, z would equal x minus np divided by the square root of npq. So let's just compare that to our normal z transformation. We had x minus mu over sigma. And that is as n is large, so we usually say as n approaches infinity, although it doesn't have to be quite that large for this to work. And it is the standard normal distribution. Okay, so if it's bell-shaped and n is large and p is not close to 0 or 1, the normal is a good approximator of the binomial. But in addition to that, it also provides a fairly good approximation when n is small and p is close to 1/2. Okay, to illustrate the normal approximation to the binomial distribution, we draw the histogram. So the square columns or blocks are the histogram. And then we superimpose the normal curve on top, so you can see the curve on top of the histogram. This is for binomial x 15, so our n is 15, so relatively small, but we are close to a half, so p is equal to 0.4. So you can see we have 0 through 15, and you can see the histogram where the numbers are on the center of the base. So when we look at mu, so mu is equal to np is equal to 15 times 0.4, so this is equal to 0.6. And when we look at sigma, square variance, we have NPQ, so that's 15 times 0.4 times 0.6, so that's equal to 3.6. And so the exact probability that the binomial random variable x assumes a given value x is equal to the area of the bar whose base is centered at x. So for an example, the exact probability that x assumes the value 4, so if we're going to look at 4 on our graph, it is the area of the rectangle of that base. So before we get into those calculations, we're going to look up on the table 8.1 from the book, and that is our binomial distribution table. And if you look it up, we're going to look up at n equal 15, x equal 4, and p equal 0.4. So from the binomial table, this probability is equal to 0.1268. Okay, so now we want to look at this rectangle 4. So if you see we have a 3 and a 5, so the edge, we're going to create an interval. So the edge of the rectangle is 3.5 to 4.5. That would be our 4 rectangle. So we are going to calculate 2z values. We have a z value 1, and that's going to be 3.5 minus 6 divided by the square root of 3.6, and this value is a negative 1.32. And then our z2 is going to be 4.5 minus 6 divided by the square root of 3.6, and this is equal to a negative 0.79. So when we go to our z table and we find the probabilities of each of these two values, the probability of this is 0.2148, and the probability of a negative 1.32 is 0.0934. And when we subtract the two, we get the probability of 48 minus 0.0934. This is equal to 0.1214. So again, by creating that interval, we have two probabilities. So a 0.1214 approximating a 0.1268, they're very close. And so we would say that is a good approximation when we're talking about probability of the normal for the binomial. But what we had to do is we created the interval, and we added the 0.5 to our x. We added and we subtracted a 0.5 to our x to create the interval. So we call this 0.5 the continuity correction. In our illustrations of the normal approximation to the binomial, it became apparent that if we seek the area under the curve to the left of x, so if we are less than or equal to x, it is more accurate to use x plus 0.5, and this is called a continuity correction. And so we can write this as the probability that x is less than or equal to little x is equal to the binomial is equal to z less than or equal to x plus 0.5, the continuity correction, minus np over the square root of npq. And we just demonstrated that in our example. Okay, now let's look at our histogram that we had with our normal distribution imposed for our binomial of x 15.4. When we look at that, and when we look at this, if we wanted to find the probability that we would be between 7 and 9, so if we wanted the areas 7 and 9, we would use the values of 6.5 to 9.5. So you have to look at your curve, your histogram, and where your two endpoints would be. So we would do the same analysis doing a Z1 and a Z2 at 6.5 minus 6 over the square root of 3.6 and a 9.5. So if we wanted to find the probability that x is between 7 and 9, we would use 6.5 to 9.5. If this said the probability of 7 less than or equal to x and less than 9, we would use 6.5 and 8.5. So now when we're estimating the for our two x values in our z equations, so it matters if you have the equal sign or not. If you're just less than 9, you would be looking for 6.5 to 8.5 because you would be less than 9 for the second scenario. Okay, let's talk about the sum of normal random variables. So if big X1, X2, Xn are independent random variables having normal distributions with means mu1, mu2, mu-n, and variances, then the random variable y equals a1, which is a constant, x1, plus a2, x2, an, xn, and has a normal distribution with mean. So mu y is equal to a1 mu1 plus a2 mu2 plus an mu-n, and the variance would follow suit. So that'd be a1 squared sigma square 1 plus a2 squared sigma square 2 plus a squared sigma square n.